Okay, let's get started with our first ideal gas law problem. This one is going to be a straightforward plug and chug problem. How do you know that you need to use the ideal gas law instead of Boyle's or Charles or combine? Mainly because the pressure isn't changing, volume isn't changing, temperature isn't changing. This is one scenario, and they're asking you for amount of a gas. Okay, so let's take a look at this problem here. It says a 50.0 cylinder of nitrogen gas has a pressure of 17.1 atmospheres at 23 degrees Celsius. What is the mass of the nitrogen in the cylinder? Now, the ideal gas law doesn't give you the mass, but it gives you the moles. And then from the moles, obviously, you can do molar mass to get the mass of the nitrogen. So PV equals nRT. PV equals nRT. Remember, if we're going to use the R that I was telling you guys about, 0.0821 atmospheres liter over mole Kelvin, our pressure has to be in atmosphere. Well, good thing they gave us the pressure in atmosphere. So we'll write 17.1 atmospheres. They gave us the volume in liters. So we'll write 50.0 liters. N is our unknown. That's what we don't know. We have our R. Our temperature is in Celsius, so we have to add 273 to this in order to convert it to Kelvin, and that would be 296 Kelvin. Yep, okay. Now, plug and chug, we plugged them in. Now we just manipulate the equation and solve for N. What would N be? So N would be 17.1 times 50 divided by 0.0821 divided by 296. Can everybody see that okay? All right, putting in the units just to make sure that everything cancels beautifully. This is atmospheres. This is liters. This is Kelvin. This is atmosphere, liter over mole, Kelvin. Okay, so atmospheres cancels with atmospheres. Liters cancels with liters. Kelvin cancels with Kelvin. And moles is in the denominator of the denominator, which is the numerator. So good. That's what we want. We want moles in the end. All right, so you pick up your calculator and you plug it in correctly. Just make sure I have this. 17.1 times 50 divided by 0.0821 divided by 296. All right, let me see if I plugged in my numbers right without my glasses. All right, so I've got, let me double check. 17.1 times 50 divided by 0.0821 divided by 296. Okay, I have 35.2 moles. That's a lot of moles. 35.2 moles. All right, but that's not what they want. They want grams. So 35.2, so oops, I can't write properly. What is wrong with me? Okay, 35.2. I know I said 35.2, but I wrote 32. So 35.2 moles. Good. So 35.2 moles of nitrogen. Now remember, nitrogen is a diatomic molecule. So if you go to the periodic table, nitrogen is 14 and you have two of them, so that's 28. So 1 mole of N2 is 28.0 grams. Moles will cancel. Now get your calculator 35 times 28 is equal to 980 grams of nitrogen. I may have rounded a bit too fast here, but that's good enough, good enough. 980 grams of N2. If you kept all your sig figs and didn't round too early, you probably would get 985 grams of nitrogen. I think that is the more correct answer. You know what? 35.2 times 28. Yeah, it's because I used 35 instead of 35.2. Go figure. My brain's on a different plane today. So actually, the way I have it, it'd be 986 grams of nitrogen. Okay. So if you got 980 or 985 or 986, you're doing okay. All right, so that's a simple, straightforward, plug and chug ideal gas law. Now, let's take it a bit of a step up. Let's kick it up a notch. All right, let's kick it up a notch. We're going to use the ideal gas law to figure out the molecular weight of an unknown compound. All right. If you remember, molecular weight or molar mass is grams per mole. So in order to figure out the molar mass of something, which is the same thing as the molecular weight is AMU, molar mass is grams per mole. Molar mass is grams per mole. If they give us the number of grams of an unknown compound, and we can use the ideal gas law to figure out the moles, all we have to do is take the grams they give us divided by the moles that we figure out, and we've got the molar mass of the unknown gas. So here is a problem. So this would be under the big category of determination of molecular weight using the ideal gas law. I just saw over here that I've got to deal with also Avogadro's law. I will do that and STP, but let me finish a couple of things before that. All right, here's the question. You have a 15.5 gram sample of some gas, of an unknown gas. And you have it in a container that is 5.75 liters, okay? And the temperature is 25 degrees Celsius, and the pressure is 1.08 atmospheres, okay? And your job is to find the molar mass. Well, when you get a problem like that, and I promise you will get a problem like that on the test and in the homework. How do you figure out molar mass? So the first thing you want to do is find moles. And like I said, once you've got moles, you take the grams that are given to you, grams divided by moles, that gives you your molar mass. All right, so PV equals nRT. Why are we using PV equals nRT? Because it's the only gas law that gives you moles right now, right? So we've got our pressure, which is 1.08 atmospheres. We have our volume, which is 5.75 liters. N is our unknown. We know our R, 0.0821. Try to memorize it, guys. Atmosphere, liter over mole, Kelvin. And then we have our temperature is 25. We're going to add 273 to it. So that's 298. 298 Kelvin. Okay, manipulate the equation and solve for N. Let's go ahead and do the math here. Hopefully this time I will plug numbers in right. N is equal to, so basically this times this divided by this divided by this. So 1.08 times 5.75 divided by 0.0821 divided by 298. Why am I pressing divide? Because both of these are in the denominator. Anytime I have anything in the denominator, I just press the divide button. All right, so your N is 0.2 5, how many sig figs do we have? 3, 5, 4 moles. Okay, this is how many moles I have. So what I'm going to do is I'm going to take my grams, which is 15.5 grams, and divide it by my 0.254 moles. Okay, that's how you get molar mass. Anytime you're given grams of an unknown substance and you manage to find moles, grams divided by moles is molar mass. You're going to be using this concept a lot throughout the semester in different chapters. So it's always the same thing. They give you grams, you have to do a problem to find moles. Grams divided by moles, that's your molar mass. Okay, so plugging it in, 15.5 divided by 0.254, and you get 61.0 grams per mole. And that would be the molar mass of the unknown gas. Okay? Good. The other tweaking of the ideal gas law is to find density. So you can just use ideal gas law to find moles, and use that to find molar mass, or you can use the ideal gas law to find density. Now you guys know what density is. Density is mass over volume. Well, how does that work with the ideal gas law? Well, think of it this way. The ideal gas law is PV equals nRT. And for density, we want grams per liter. That would be the density of a gas is usually in grams per liter. Okay, but there's no grams here, there's moles. So our goal is to get moles over liter on one side and everything else on the other side. And once you've got your moles over liter on one side, you can then use molar mass to convert moles to grams. And then you'd end up with grams per liter, which is density. Okay, so how do we do that? We manipulate the equation. We bring this down here and these guys over here. So P over RT is equal to N over V. That will give you moles per liter, which is halfway to getting density, which all we have to do is then use molar mass. All right, so here's a problem. I have ozone. Ozone is O3. So I know the identity of the gas, so I'm going to be able to use molar mass. I have some ozone. The temperature is 50 degrees Celsius, and the pressure is 1.75 atmospheres, okay? And my problem is I need to find the density. Okay, great. I have the pressure is 1.75 atmospheres. I have R 0.0821 atmosphere liter over mole Kelvin. And I have the temperature is 50 degrees. I'm going to add 273 to this, and I end up with 323 Kelvin. Okay? The kelvins cancel, the atmospheres cancel. This is denominator of the denominator becomes moles per liter, which is exactly what we want. So we plug in the math, plug in the calculator. I have 1.75 divided by 0.0821 divided by 323. Anything in the denominator, I press the divide button, and I get 599 moles per liter. Okay, I'm just going to leave it like this for a minute. Now, I want it to convert that to grams per liter. So I'm going to put it over here, 0.06599. I'm going to pay attention to sig figs in a minute, guys. Moles per liter. I want to convert moles to grams. So 1 mole of ozone is 32 and then 16, 48. 48.0 grams of ozone. So I'm going to take that 0.065 0.6599, and then I'm going to multiply it by 48, and I end up with 3.17 grams per liter as the density. Oops. Okay, good. So we're done with ideal gas law and its applications for now. The next video will start off talking about Avogadro's law and STP, and then move on to, I guess, gas stoichiometry. Okay.